Let's take a look at Chapter 3, Applications of Differentiation tonight. We're going to start with a new term, the word extrema on an interval. So an extrema is defined as a maximum or minimum point on a curve. Extrema can occur in two different kinds of situations. We can have relative minimum points, or we can have relative maximum points. Relative minimum or maximum points occur at peaks or valleys on a curve. Sometimes we call relative extrema local extrema. Let's take a look at the graph that we have above. On this graph, we can see that there are peaks and valleys in the graph. So let's go ahead and identify those points. We see that this point right here, as well as this point right here, both of those would be called relative minimum points. They're relative because they're the minimum points in that section of the graph. We also have another point that will identify this one right here on the y-axis. That one we're going to call a relative maximum point. Now, as we go through this chapter, we're going to see how calculus is going to help us to identify those relative minimum and relative maximum points. As we can see, the two red points actually look like they're tied for how low they both are. So they're both going to be called relative minimum points. Now, when a peak or a valley is smooth or rounded on a graph, we're going to see that the graph has a horizontal tangent at that point. So let's draw a graph like this. There are my axes. And if I draw in a curve that has a peak or a valley that is smooth or rounded, at the place where it has that peak or valley, the lowest point and the highest point, I'm going to see that that curve has a horizontal tangent. Can we remember that where I have a horizontal tangent is where my derivative of the function is going to equal 0, because the derivative just stands for the slope. If, on the other hand, we have a peak or a valley that has a sharp turn, then what that tells us is that we end up having a function that is not differentiable at that point. So let's take a look at what that's going to look like on our graph. We might have something that looks like the following. Again, here are our axes. We can go ahead and graph something that would have a sharp turn. So for example, it might have, remember how we called this a cusp? A cusp is a place where I have a peak or a valley, but the graph is not differentiable there. So right here I see that that point is going to be a relative maximum point, but at that point the derivative does not exist. Think about when else I could have a sharp turn. Our favorite graph, of course, is the graph of the absolute value function. So for example, if I've got a graph that looks like this, where my sharp turn is right here at C, then at that spot I can't take the derivative. I still see that I've got a sharp or pointed part of my graph, but the derivative again does not exist at that spot. So I'm going to say then that I can have relative mins and maxes where I have a peak or valley that is smooth or rounded, but I can also have relative mins or maxes when the peak or valley is sharp or pointed. So next we have a really important definition in calculus. This is the definition for critical numbers. If f is a function that is defined at a c value, if the derivative of f at c is equal to 0, or if the derivative of f at c is undefined or does not exist, then what we're going to say is that c is called a critical number. So we can have any number of critical numbers on a graph. A critical number is going to be any place where the derivative is equal to 0, or where the derivative is undefined and possibly does not exist. The following theorem, Fermat's theorem, says that relative or local extrema can only occur at critical numbers. So let's take a look at the example, f of x is equal to x to the fourth minus 8x squared plus 1. What we'd like to do is find the derivative of this function and then evaluate the value of the derivative at each of the relative extrema that we see on the graph. So the graph that I have in the notes here is the graph of f of x equals x to the fourth minus 8x squared plus 1. So let's start by taking the derivative of this function. So for our derivative, this is a nice easy derivative using the power rule. So f prime of x is equal to 4x to the third minus 16x. The derivative of 1 is, of course, 0. Now, when we take a look at our graph here, we see that we've got a critical number, or I'm sorry, it's actually a relative maximum at 0, 1. We've got a relative minimum at the point 2, negative 15, and another relative minimum at this point right here, negative 2, negative 15. So our goal is to evaluate what the derivative is equal to at each of those points. So let's start with f prime of 0. When I substitute 0 into my derivative, I of course am getting 4 times 0 minus 16 times 0, and I see that the derivative turns out to be 0. That tells me that 0, 1 is a critical point. X equals 0 is a critical number because the derivative at 0 is equal to 0. Let's do the same thing for the derivative at the number 2. So we're going to say 4 times 2 cubed minus 16 times 2. That's giving me 4 times 8, which is 32, minus 32, which also gives me a derivative of 0. And lastly, let's take the derivative at negative 2. So we're going to say 4 times negative 2 cubed minus 16 times negative 2. So 4 times negative 8 is negative 32. Negative 16 times negative 2 is positive 32. Adding those together, again, we get 0. So we can say that all three of these points are going to be critical points because the derivative is equal to 0 at each of them. Now we're also going to take a look at some examples in Chapter 3, Section 3 as well. We're going to look at increasing, decreasing, and the first derivative test. Now, when I see that the first graph is increasing, in calculus, we're going to say that this graph is increasing because no matter where I look at it, when I draw in a tangent line, or when I look at the graph of the function, the graph of the function is actually going to have a derivative that is positive. So everywhere where the derivative is positive shows me that I have an increasing function. On the right-hand graph, I see that this time my graph is decreasing. Every place where my graph is going to be decreasing, when I draw in those tangent lines, notice that those tangent lines have negative slopes. Slope thinking the same as derivative, so we're going to say the derivative for those are all negative or less than 0. Now we see some other examples of increasing graphs. So first of all, this one on the left side is going to be an increasing graph. because no matter where I draw in the tangent line, I see that the tangent line, or the derivative of the function, is positive. On the graph on the right, I hope you identified that as a cubic function. Whenever I draw in that tangent line, I'm seeing, I'm kind of missing my tangent line a little bit there. I'm seeing that the tangent line turns out to have a negative slope, so f prime is less than 0. Now, there's one exception to that right here at the origin. At the origin, the derivative would equal 0, so it has a horizontal tangent there. But everywhere else, this graph is a decreasing graph because I see that the function has a derivative that's negative. And on the graph on the left, that was an increasing function because every place on that graph, the derivative was positive. Now, we're going to go ahead and use these next two graphs and identify for these our relative mins and maxes, and from that be able to tell where I have an increasing or decreasing function. So first of all, I see that I have at -1, 2, that looks like I've got a relative maximum point. At 1, -2, that's looking like a relative minimum point. So now, looking at the graph, before the number x equals -1, I see that that graph is going uphill, it's increasing, and every place along where I've just colored in has a positive slope or a positive derivative. Between -1 and +1, I see my graph is going downhill. So if it's going downhill, it's a decreasing function, and that corresponds with a derivative that's negative. Finish it off with all the points after x equals 1. Again, I'm going uphill, so that tells me that my function is increasing in that section. So we are increasing from the number 1 to infinity. We also were increasing back here from -infinity up to -1. And in the blue section, we are decreasing, and that's from -1 to 1. Now, generally, we don't include the endpoints when we're talking about intervals of increasing or decreasing. So why don't you try the example that's on the right side, draw it in your notes, and see if you can label where this graph is increasing and decreasing. Take a few minutes, and then we'll take a look at what the answers are for this. I'm going to identify that there's a minimum point right here, and we're going to call that at -1.5, -5.5. And we're going to call this relative maximum point up here at 1.5, 5.5. So go ahead and write down your intervals of increasing and decreasing. I am getting that this graph is decreasing over the interval from -infinity to -1.5. And again, I'm not including those endpoints. Also decreasing on the interval from 1.5 to infinity. In between, the function is increasing, and that's happening from -1.5 to +1.5. Now again, we're going to use calculus to test for increasing or decreasing functions. So in previous courses, you've just been able to look at a graph and say, it's going uphill, so it's increasing, or it's going downhill, so it's decreasing. For us in calculus, there's a reason that it's increasing or decreasing, and it's based on the derivative. So if I've got a function f of x, and it's continuous on the closed interval from a to b, and differentiable on the open interval from a to b, I will be able to tell that the function is going to be increasing if f prime of x is greater than 0. So that's where my derivative is positive. On the other hand, if the derivative is negative, that's going to tell me that my function is decreasing on that interval. And if the derivative is equal to 0, then the function is going to be constant on that interval. Now we might want to pause the notes so that we can write down this test for increasing or decreasing functions. Now let's take a look at the test for the first derivative test. The first derivative test says if C is a critical number, if f prime changes from negative to positive at C, then the point C comma f of C is a relative minimum point. So picture this. We've got a graph where my derivative is changing from negative to positive. So that tells me that my graph is downhill or decreasing and then switching to increasing. So at the place where it switches from decreasing to increasing, or from a negative derivative to a positive derivative, that tells me that this point will be a relative minimum point. Part 2 says if f prime changes from positive to negative at C, then the point C f of C is a relative maximum point. So let's draw this one. So this time I've got my derivative changing from positive, so my function is increasing, and then I change over to a negative derivative, so my function is decreasing. This is happening at C, so that tells me that this point is going to be a relative maximum point. We're going to be identifying these values on a number line. We're going to say if I have a C value where my derivative switches from negative to positive, that's going to tell me that I have a relative minimum at C. If, on the other hand, I have a C value where my derivative switches from positive to negative, that's going to tell me that the C value must have been a relative maximum point. So we are going to have 5 steps for finding the extrema of a function using calculus. Our first step is going to be to look for where the derivative is equal to 0. That's going to allow us to find our critical numbers. Now there's one more thing that we want to include here though, because critical numbers are also places where the derivative is undefined. So we want to look for where our derivative is either equal to 0 or undefined. Once we find those critical values, we will set up a number line. And on our number line, we will put any critical values. I'll call them C1, C2, C3. I will pick test points in between these numbers, and I will decide if the derivative is positive or negative in between. Any place where the derivative is positive, that's going to give me an increasing portion of my function. Any place where my derivative is negative, that's going to give me a portion of my function that's decreasing. If my function if my derivative changes from positive to negative, that's going to tell me that that critical number is a relative maximum. So that also occurs right here at C3. If, however, my derivative changes from negative to positive, that critical number is going to be a relative minimum point. So what we have just done then, using that sign analysis chart, is classified each critical number as a maximum or a minimum by looking at the derivative value before the critical number and after the critical number. After we decide if the critical number is a minimum or a maximum point, we will want to find the function value. Now, of course, to find a function value, we have to go back and use our original equation. So then we'll have an ordered pair. Go the next step, and again, use your sign analysis chart to tell the intervals where the function is increasing or decreasing. So let's take a look at example number 1 and go through these steps. We want to start by, first of all, it says find the critical numbers and extrema for f of x equals x cubed minus 3x squared. So step number 1 is to identify our critical numbers. So we're going to take our derivative and we're going to set that derivative equal to 0. So finding the derivative, first of all, we've got 3x squared minus 6x. Let's set that derivative equal to 0 because that's the definition of a critical number. You'll notice that 3x squared minus 6x would never be undefined, so my only choice for a critical number here is where the derivative is equal to 0. To solve this, I'm going to factor out a 3x, and I'll be left with x minus 2. So when I set this equal to 0, I end up with two critical numbers, x equals 0 and x equals positive 2. So these two are both critical numbers. Step number 2 is going to be to go ahead and put this on a number line. So on the number line, this is our sign analysis. We are going to be focusing on these critical numbers, but also on the derivative value between these critical numbers. So I'm going to put 0 on my number line. Oh, that doesn't look like a very good 0, does it? Let's fix that. And let's put the number 2. Now we have to label our number line with an F prime so that the person that's reading our paper can tell that I'm analyzing the derivative. I'm going to pick a test point. Test point before 0 would be negative 1. Let's plug negative 1 into that first derivative. I like to put it into the factored form because it's easy to see whether I have positives or negatives. So 3 times negative 1 gives me negative 3. Negative 1 minus 2 gives me negative 3. A negative times a negative gives me a positive value for my derivative before 0. Go between 0 and 2, for example 1. At the number 1, 3 times 1 is positive, 1 minus 2 is negative, so therefore I end up with a negative derivative between 0 and 2. After the number 2, I can pick 3. So 3 times 3 is positive, 3 minus 2 is positive, positive times positive is positive. So from this, I can then see that 0 must turn out to be a relative maximum point because my derivative switches from positive to negative. 2 turns out to be a relative minimum point because I see that my derivative switches from negative to positive. My intervals of increasing are going to be from negative infinity to 0, and again from 2 to infinity. My interval for decreasing, there's just one this time, so my interval of decreasing is going to be from 0 to 2. And again, we don't include the endpoints on these. Let's just take a look at one more example. So if I've got f of x is equal to x to the 4th minus 2x squared, I'm going to do step number 1, which is to find my critical numbers. So I want to say, take our derivative, f prime of x. Let's set it equal to 0, but first I have to find it. So that's going to be a 4x cubed minus 4x. So set that equal to 0. I can factor out a 4x, and I'm left with x squared minus 1. Now I've got options here. I can either solve the quadratic or I can factor further. I'm going to set each factor equal to 0, so I'm getting x equals 0 and x is equal to plus or minus 1. So all three of these values are my critical numbers. I go to my number line, and I'm going to put the negative 1, the 0, and the 1 on my number line and evaluate the derivative in each section. Now, when I pick a number, I'm going to go in each section. So I'm going to say negative 2 comes before negative 1. 4 times negative 2 is negative. Negative 2 squared minus 1 is positive, so a negative times a positive is negative. Between negative 1 and 0, for example, negative 1/2, 4 times negative 1/2 is negative. Negative 1/2 squared minus 1 is also negative, so I get a positive in this region. Between 0 and 1, for example, 1/2, 4 times 1/2 is positive. 1/2 squared minus 1 is negative, so positive times negative is negative. And after the number 1, for example 2, I get positive, positive, which gives me a positive derivative. This tells me that negative 1 is going to be a relative minimum point because my derivatives switch from negative to positive. 0 is going to be a relative maximum point because my derivative is switching from positive to negative. And let's fix this. I want to put it at the number 1. So the number 1 turns out to be a relative minimum because I see that my derivative switches from negative to positive. My intervals of decreasing are going to be from negative infinity to negative 1. So that's where my derivative is negative. Also happens here between 0 and 1. My intervals of increasing are going to be any place where the derivative is positive, so that happens between negative 1 and 0, and again from 1 to infinity. Now you'll notice that these intervals are interval notation, so we're talking about x values where the function begins to increase and stops increasing. Now, for each of these points, I left this off on the last example, but we should have gone back and found our original points. So my relative minimum point, if I plug negative 1 into my function, I'm getting a 1 minus 2, so a negative 1 as my y value, and that's a relative minimum point. I have another relative minimum point when x is 1. And again, I'm going back to my original function. So come back up here, plug 1 in, and I see that my function value at 1 turns out to be negative 1 as well. So I have 2 relative minimum points. My relative maximum point is occurring where x is 0. Plug that into my original, and I see the y value is 0. So I have 1 relative maximum point at 0, 0. Thanks for working so well today. Work on your homework, and we'll discuss more of these tomorrow.